interval.
All right, let's get started then.
Difference actually.
Just
by making it more exact.
So my name is Alon. Good morning again. I'll be talking about how to draw a circle, which is a little bit tongue-in-cheek, but not totally. So I hope to convince you that there's some different ways of drawing circles using mathematics, and some of them are useful for different purposes, and some of them are well known, and others maybe not so. So if you know everything I'm talking about, we'll just go faster and get to places where I hope you're unfamiliar with, and if not, we'll go slow. That's fine. So this is a line, low line, low class. It's a geometric figure, and right now it doesn't have any numbers on it, but if I just do this, all of a sudden becomes a number line. So presumably this is something you're familiar with, and I guess you guys know where all the integers are. And if one thing I'm never sure of is, how do people think about rational numbers on the line? Like if I had you imagine or draw for me, like where are the rational numbers? Are they all over the place? Do they cover the line? Do they, like, if I had one of you come over and draw the rational numbers, what would you do? How do you draw them? All the rational numbers, where are they?
Right, filling the line.
They're filling the line? So you draw them like this?
They do not fill the line.
You would have to talk about the fact that it's, using that lingo of like it's a dense system.
Yeah.
You can't really talk about where they all are because they're all infinitely many in between 1 and 2.
Right.
And there's also infinitely many irrational numbers
Yeah.
between 1 and 2, so we kind of stop there.
What's more, rationals or irrationals?
Irrational.
What do you guys think? Irrationals. Yeah, why? Do you know why? Have you guys heard about countable sets and non-countable sets?
I've done this in the past.
It doesn't matter for today. We're not going to be talking about this, but in some sense, there are way more irrational numbers than rational numbers. So if anything, the rational numbers are kind of meager or sparse. Like one way to think about them is like this. Well, like many points, like grains of sand on the line. Like they're all over the place, but they leave plenty of holes. Anybody know one hole?
Square root of 2.
Yeah, where is it?
Square root of pi.
Yeah. Oh wow, that's yeah. Square root of 2 is somewhere around here, and I remember when I was a school kid, my teacher showed us how you can draw a square of side length 1 here, and just take a compass and kind of just drop it over here, and the place where the compass lands on the line is irrational, and that kind of blew my mind because like you do something very simple and you cross the line in a point which doesn't have any rational name. That's kind of a simple geometric construction that shows that the line has holes. Of course, and as you said, there are many other irrational numbers. So we got kind of used to the fact that the line is continuous, and we kind of know that there are real numbers on the line. That if you look at their decimal expansions, it's infinite and non-repeating. The Greeks many years ago did not know all about this, and they thought all numbers were rational. So the Greek line would look something like this dense set of points. Again, they didn't realize that, but it's not really like a full, smooth, continuous line. It's kind of a collection of grains of sand. So this is, again, hopefully all familiar to you guys, and this is in 1 dimension. And then, many years after, somebody came along and invented this thing. And just like this was the number line, this is like the number plane. We now have 2 lines, and we can describe every point in the plane by specifying 2 numbers, right? Say 3 and 2, so there's a 3, 2. And again, Cartesian plane, hopefully familiar to everybody. Once we have that, we can start doing some really nice things using formulas, because we can now specify all kinds of relationships between x and y and see which points satisfy those relationships and which points do not. So if I had you, for example, tell me where are all the points with y equal x. So where are those?
0, 0.
Straight line. 0, 0 is one of the points, right? But there's many others, right? So y equals all the points that satisfy y equals x are right here. Roughly. Right? And how about, for example, if I had you think about this one? Where are all these points? Everybody knows? Parabola, right. And what about this one?
Parabola opening to the right.
Yep. Like so. Yeah, this confuses a lot. So how would you use formulas to draw a circle?
X squared plus y squared equals.
X minus h squared.
Right. Wait. So I'm hearing some suggestions. So yeah, let's start with a simple circle. So we're going to make it very, very simple, and I'm going to be talking about the circle of radius 1 for like the next hour. And then we'll graduate to the circle of radius 2. Well, square it. So, this circle, I think I heard you guys make some suggestions. What are it?
X squared plus y squared equals 1.
Okay, x squared plus y squared equals 1. That's a fantastic formula for drawing a circle. Everybody agree that this is a circle? Yeah? Everybody knows why? Why? Which theorem helps us? Yeah, Pythagoras theorem, right? So let's make it bigger. Cartesian plane here. So we have our circle of radius 1 right here. And for any point on the circle, if we look at the x coordinate and the y coordinate, we have that x squared plus y squared is just 1 squared, which is 1. So this is a pretty good formula. One problem with this formula is that what it does, it says something of a pair of numbers x and y, which is either true or false. Like every point in the plane x, y that I propose, you can test it with this formula and say yes or no. So if you were, for instance, a computer, and I gave you this formula and said, please plot whatever satisfies this, all you could really do is just scan the whole plane, point by point, and for each point either say, oh yeah, that's a good point. That's a good point. That's not a good point. That's not a good point. And after you scan the whole plane, you get the circle. What this doesn't really do is allow the computer to say, oh, because this formula doesn't make it obvious that this is even like a curve. Like who knows? Maybe it's like the whole area of points that satisfies this. Maybe a thing satisfies. I don't know. Like if I were a computer and had no kind of understanding of geometry, the only thing I could do with this thing is just try point by point, and eventually I would have a circle. So is there a better formula, maybe a variation of this, that helps me understand that there is like a curve involved here? Yeah.
Well, I don't know if it helps understand the curve, but if you just isolate y and
Yeah.
you use like the plus or minus case, plus
Yes.
and minus.
So isolating y, like so, does certainly help. And why does this help? Well, it helps because now we have one parameter x, which we can control at will. So imagine like I have a knob here that controls x, and as I turn the knob, the x thing here just sweeps back and forth over the x-axis. And now I don't have to think like which point satisfied or not satisfied. For every x, I have a formula which tells me what y is. Well, there's two y's sometimes, and sometimes there isn't any, but like at least I know very specifically what I'm supposed to do. For this x, I'm plugging it here, I get nothing. So this is the square root of 1 over square root of 1 minus something too big, and it's negative. For this particular x, if x equals 1, I get the single y, which is 0. And for this particular x, for example, if x equals 1/2, I get y, which is what?
Square root of 3 over 2.
Square root of?
Square root of 3 over 2, I think.
Square root of?
Yeah.
Oh yeah. Okay. Right? So for and this one as well, right? The other one over negative square root of 3 over 2, right? So this is useful for a computer. Like it can scan just the, instead of doing the two-dimensional scan, it can do a one-dimensional scan. Try all the x's, and for each one, there is a y.
It also restricts your input too.
It also restricts my input, because I can
Yeah.
look at this and I can clearly see that there's no point in having x either greater than 1 or less than -1, so that helps as well. One problem with this formula also is that though it doesn't really capture the kind of, it's not uniform. In the sense, if you really did this with a computer, what would happen is that you get a circle that looks something like this. So computers cannot actually scan the whole real number line, right? It's too many numbers. So what they do is they sample. And if you sample the circle, what you get is something that looks a little bit like this. You see why?
Yeah.
Why is it denser here than it is here? So because the slope, right, over here, if you take x that are close enough, you'll actually sample the circle at a very good rate. Over here, as you jump, say, a tenth in x, this almost jumps by a tenth as well. So the sampling of the circle is not uniform.
Wait, that's... If you were to test uniform distances along the x-axis, the dent's probably at the top and the bottom, not on the side.
No, it wouldn't.
No.
No, let's see why.
Wait,
Take close axis
why am I missing
here.
that?
So
Yeah, those intersections are farther apart than... Yeah,
Oh.
on the sides the intersections are farther apart.
why am I? That's actually correct.
Yeah, on the TI-84 when you graph it, they always miss
You're
it.
right.
Right, that's the point.
You're right.
Why?
Yeah, absolutely right. I'm sorry. Of course, the slope here is bigger in absolute value, so this is actually a less dense sampling than it is here. I apologize. You're absolutely right. It's the exact opposite.
But the board had just turned, right,
Hmm?
90 degrees. That was the problem.
Yeah,
Yeah, sorry, you're right. But at any rate, it's not uniform.
sure.
So it's not sampling the circle at a uniform rate. It's like giving us. I mean, again, it's not too bad for the purpose of drawing circles in real life. This is if you plug this formula into a computer and have it plot the circle, you'll get a pretty good circle. But there's something anesthetic about it. So which formula I could use if I really wanted to sample the circle in a uniform fashion, actually have like this, the computer do that. Uniform motion.
R equals 1? On a polar
Well, R
coordinates?
equals 1, well, okay, so R equals 1, that's a good point. So R equals 1 makes various assumptions. R equals 1 is a very good formula for the circle if you know about
Polar
polar
coordinates.
coordinates. So yes, it is correct that there's another way of naming the points on the plane, instead of with the x's and y's, with r's and thetas. But you have to know about r's and thetas to do that. That's kind of cheating. Because circles are very, very, they fit very nicely with the polar plane. So many computers don't have any idea about the polar coordinate system. So what do you do then?
Could you isolate the x also and plot them at the same time?
Well, how would that work? That's an interesting idea. Like,
Huh.
but then you have, so y is the square root of 1 minus x squared, and x is the square root of 1 minus y squared, and what do I do then?
Well, maybe
I just wanna
the
make sure I
two
understand. Are you
dense
saying-
areas would complement each other and you get
Oh, you
four
could
dense
like.
areas?
So you're saying like a two-pass scan, where you do the first pass.
Yeah, I'm not
Why
convinced
is
this would be.
I don't think it was
either.
uniform though.
Yeah.
Yeah.
So
We
why
just
not
balance
just use
it.
symmetry then?
Okay.
The same thing. I mean, you only need 1/4 of this when you think about it, but then of course you don't really need 1/4 of this. You only need half of the coordinate. I mean, so you could do repeated symmetry.
Right, but does it ever end? Like, is there any point where I have enough of the circle to say, well, let's plot this
It would be,
small arc and then just replicate it? But how do I plot the small arc?
right, I mean, that's a question.
So ideally, there would be a formula with some parameter t, such that as I let t run between some values, for every t I get x, which is some function of t, and y, which is some other function of t, and that gives me the point of the circle. And as I scan the t values, as I fiddle the knob of t, the point here just goes at a uniform rate. So there's got to be such a formula.
I mean, like x equals sine of t and y equals, x equals cosine of t.
Exactly. Trig functions familiar?
I'm not initially sure though how that's any different because it's going to be doing individual angles.
Hang on.
But
Let's
the
just
angles
figure
are-
this for a second. First of all, let's
the angles are
ask ourselves,
equidistant. So
is that a good formula or pair of
1
formulas
degree apart.
for a circle? Does this yield a circle?
In and of itself, no.
Well, yeah.
These two.
Yeah.
These pair functions
Together, okay.
together.
Yes.
Okay.
As
Yeah.
t scans the value, which values?
0 to 2 pi,
0 to 2 pi.
not including 2
Yeah, you don't actually know. That starts. So, first I want to make everybody is totally clear and happy with the fact that these formulas do give us a circle. Do they? It's the same triangle as one before. It's just, this is t. It's just a shorthand for the angle theta. If this is the angle theta, x is the cosine of theta, and y is the sine of theta, right? So for every t or theta between 0 and 2 pi, if I calculate these two numbers and I plot them, I get a point in the circle. And if I scan the whole range between 0 and 2 pi, I'll get the full circle. So, and this is uniform in the sense that as you move the angle by 1 degree, you get exactly equally spaced
So
points on the circle.
for t belonging to the integers, then, I mean
Sorry, for?
for integer values of t, you're not going to do like
Oh no,
Integer
integer
t.
values are not a good idea. I mean, this whole range is between 0 and about like 6. So if I only scan t with integer values 1, 2, 3, 4, 5, and 6, I'm gonna get what is 1? Do you guys know?
57
57.
degrees.
Yes, that's somewhere around that. That's about here. Roughly. Right?
That's convenient.
T equals 1, it will be here, t equals 2 here,
Right before.
3,
Yeah.
4, 5, and 6, and that's it. That's not good. That's not a very good sampling. It is a sampling, and it is uniform. Those distances are all going to be 57 degrees, or 2 pi, or like a single radian, right? But if you scan more densely, if you take like t equals 0, and then t equals 0.001, and then t equals 0.002, etc., you get a pretty good sampling of a circle, and if you have the computer plot these values, you get a nice circle of radius 1.
so you're arbitrarily picking like the rational values then.
That's a good point. Hold this thought.
Okay.
We'll get there in a second. So, in some sense, these are the best formulas for drawing a circle because they're capturing the uniformity and symmetry of the circle ideally. The problem with this, of course, is that who knows how to calculate the cosine of something? Like, yes, computers don't know how to do that. But if I gave you guys t equals 0.001 and asked you what is the cosine of that, how would you go about it?
0.999.
Yeah, that's a pretty close approximation. But if I make it a little bit harder and say t equals 0.45, what then? How do you even calculate the cosine of something like that? What is like? So cosine and sine are almost cheating. They're the functions that are defined by us wanting to find those points on the circle. But actually being able to calculate them is non-trivial. We can talk about this later if you like. How do computers actually do that? Well, most computers actually they have tables for that, but there's good ways of doing this. But obviously, like if we wanted to use these formulas, the first challenge would be that they're just hard to calculate, much harder than these. Here we have to take a square root, which can be a challenge in and of itself, but like if you guys know how to take square roots of like decimal fractions or fractions. So, but what I'm going to show you, what I'd like to show you now is that all of these formulas that we used so far are almost useless if we want to ask ourselves a very, very simple question, which is the question I alluded to earlier today. Let's pretend we're Greeks. And we don't know about all of these fancy numbers. We have no idea what the square root of 3 is. We certainly have no idea what the cosine of 0.001 is. All we know are rational numbers. So, pretend now that you are a pre-Pythagorean Pythagorean Greek, and I have you plot the circle of radius 1. Can anybody give me any point on the circle? Yes.
Wait, what's your... I thought you were going to say how to draw, sorry.
No, before we draw it, just give me a point.
0, 1.
0, 1 is a good point. It's right here.
Tie your sheep to a stake.
Wait. So we have 0, 1 right here. Other points on the circle?
Negative 1, 0.
Oh, 1, 0, yeah. Right here. Other points?
Negative 1, 0.
Negative 1, 0. Right here. 0, negative 1. See, I figured this one out for myself. 4 points. That's a pretty lame circle. Any other points?
3/5, 4/5. We're not allowed to do that yet because we don't know Pythagorean theorem.
I don't know. Do you?
But you can measure that and just rotate a ruler.
Wait. Measure what?
The distance of each of those, and just take a ruler based at the origin and move it along and mark the dot.
I can certainly use a compass. And this is what they did. They did this. And this lets you draw a circle. But we're now taking the kind of Cartesian analytic point of view, and we understand points by giving them names. So yes, the Greeks definitely understood that there is a circle of radius 1. They did not think it's empty. But if you had them, hang on. If you had them name these points in the modern Cartesian way, which they didn't have, I'm mixing history here, but that's not so easy, right? So I heard one suggestion here. Do you have a question?
Well, I just want to make a comment. Ancient Babylonians knew Pythagorean triangles.
Right.
So you can use 3/5, 4/5.
Correct. You can use 3/5, 4/5, and that's absolutely right. And where is it? It's going to be about here, right? 3/5, 4/5.
It's like farther.
Because it has to be more than a half.
It's like
Yeah,
0.6, 0.8.
Yeah, I'm sorry, I'm late. Somewhere here. 3/5, 4/5. Excellent. So you guys have figured out that Pythagorean triplets have something to do with the circle. So how does this work exactly? Why? Well, we can check that 3/5, 4/5 is on the circle, right? If we square them, we get 9 over 25 and 16 over 25. If we add them up, we get 25 over 25, which is 1. Any other points you guys remember?
So 5,
5,
13.
and 12, 13.
Correct. Now, where's that? That's going to be here.
Yeah.
Like
Here.
a third and, yeah.
5, 12, 5 13th, and 12 13th. By the way, one nice thing that this does, there's a Pythagorean triangle, 3, 4, 5. There's also a different triangle, 6, 8, 10, right? Does this give me another point in the circle?
No,
It's the
same
same
one.
point. So one nice thing this does, it kind of merges together all the equivalent, similar triangles. Okay, so the thing is though, does any of the formulas that we used so far help us see those Pythagorean triangles? How do you find them? So you guys know about a few, right? 3, 4, 5, and 5, 4, 13. How many are there?
Infinite.
Infinitely many?
Yes.
If I plotted them on the circle, what would it look like?
The circle?
Do they fill in the
No.
whole circle?
It would have holes.
No, because you still have the rational number.
Right, but do I have actual like gaps? Like, is there like maybe
Not visible to the eye, but yes,
Little-
you would.
are you sure?
You're asking if, like, you're.
I'm asking, what does it look like? So if I had to come over here and plot for us only the rational points. Rational points are points whose coordinates are both rational.
Huh.
If I
I
had
think
to
you get
plot,
more near the axes than in the middle.
well, you're right. I'm not gonna.
Yeah.
Let's hold a thought about uniformity for a second. But just ask ourselves: is it really giving us the whole circle? Maybe there's like a little segment here of length 0.001 inches
That spikes out or something.
where there's nothing inside. Maybe the rational points are here and they're here, but they completely miss this segment.
Wow.
Does this happen?
Yeah, I feel like there would be a gap, like, near the axes. And
How big is the gap?
Because there aren't a lot of Pythagorean triples where the first, like, for there to hit a point near the axis, the Pythagorean triple, one of the numbers would have to be very small compared to the other two.
You mean over here?
Not
Yeah, that's a good point. So so what do you think? Do we have actual gaps?
And
This is a very-
the shape of the triangles.
This is a
for
strangely
Pythagorean triples.
basic and fundamental question. What does a circle look like to people who only know about rational numbers? it's a little bit strange that a lot of people are not like aware of the existence of this question and how to approach it. So it would be useful to have like a mechanism or an algorithm to kind of produce all the Pythagorean triplets for us, right? What I'm going to try and show you today is like the other way around. If we approach the problem geometrically, we can come up with a procedure to do that, which will give us this algorithm for producing Pythagorean triplets, and will also reveal to us exactly what the rational circle looks like. So this is.
So actually, just to follow up on my question. I mean, your earlier question was, if we have infinite number of Pythagorean triplets,
Right.
and we fill it in, is there still a gap?
Right.
Right. And then I heard you just say that we're going to generate an algorithm to find all the Pythagorean triplets, but that's not really answering the question about filling in the gap.
So we'll almost do it the other way around. We'll observe that. I'll show you some nice geometric gadget.
Okay.
Will hopefully convince you that the rational points in the circle fill it up completely.
Okay.
Nothing is missing.
I'll buy that for $1.
And then we can use this gadget to actually determine the coordinates of these points, and this will give us, as a side effect, a nice formula for Pythagorean triplets, and also a formula that's useful for many other reasons. And for some reason that I'm not sure of, it's a formula for how to draw a circle that people are not aware of somehow. It's a very useful one.
Got it. Thank you.
I have a conspiracy theory that we're not teaching it to students, and therefore we as teachers don't know about it. Because if we had, they would have a very, very easy time with things like trigonometric identities. Yeah, so like we'll get there. We'll get there.
Yeah, yeah.
So
Let's go.
let me take a pause here and just what I'm going to do now is generalize this a little bit before we go back to the circle and just tell you a little bit about what this is. So what this is part of a study, like part of a body of math known as Diophantine analysis. One way to look at this is Diophantine analysis. And what Diophantine analysis does is something very, very simple. You start with an equation such as this one, or this one, or this one. These are polynomial equations in one or more variables, in this case in two variables, but you can have more. And all of these equations are very, very easy to solve. Very easy to solve if you know a little bit like analytic geometry. Because in most cases, if you have just one formula such as this, one formula in two variables, of course it's going to have a solution. It's going to have many solutions. So, and they're very easy to find. You just guess some x and determine which y satisfied. So yes, sometimes we have square roots and they become a negative, so we can extract them, like in the circle case. But it's not hard to see the solution even geometrically. But now we're going to ask a simpler question. What are the rational solutions? Rational solutions to polynomial equations with integer or rational doesn't much matter coefficients. So in a sense, this is asking a much like this is throwing us back to 2,500 years ago. Forget about real numbers. Real numbers are hard. We barely understand them. Like who knows how to calculate them? How do you solve such equations if you only have access to rational numbers? And the surprising thing about number theory, Diophantine analysis, and all this stuff, is that asking this question turns out to be way, 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 way more difficult than approaching these equations with just real numbers. In real numbers, they're very easy. In rational numbers, some of them are not solved to this day. This one, for example, x to the 17 plus y to the 17 equals 1. Looking for rational solutions of that is exactly the same as solving Fermat's last theorem with the exponent 17. And it took humanity many, many years to realize that this one doesn't have rational solutions at all. This circle is empty, rationally speaking. This one is also not very easy to figure out. We'll talk about this later today if we get to it. It's an elliptic curve. fascinating theory of like how the rational points on this thing behave. Today we're going to be focusing on the circle. So what Diophantine analysis is I'm giving you an equation and I'm having you solve it, but only using rational numbers. And the point is this is often, always, way, way harder than solving it with real numbers. But there's still stuff we can do. And now let's talk about what we do with polynomial equations of the second degree. And here is the trick. Let's say that I have an ellipse or a is it parabola or parabola?
Parabola.
What?
Parabola.
Parabola.
An ellipse or a parabola or a hyperbola?
Hyperbola.
Hyperbola. What are these?
Conic section.
Conic sections or a circle. What characterizes conic sections?
Focus and
Focus,
They're cut from the
directrix.
double right.
So one way is to start with a cone and just cut it off, right? And in terms of equations, what sort of equations are these?
Quadratic.
Quadratic equations. So let's say we're doing now Diophantine analysis. We're trying to solve quadratic equations in how many variables? Two variables, right? And we're looking for rational solutions. So you can think about anything. Think about an ellipse or your favorite conic section. Let's look at an ellipse, for example. So first challenge. First challenge is find a rational solution. Just find one. Not all of them, just try to find one. This is often the hardest part. Okay? That's your first challenge. Suppose you found one. So we have a rational point on our ellipse that we're investigating. In this case, my claim is that we're done. As soon as we have one, we have infinitely many. And here's why. Step 2, pick a rational line. What does a rational line mean? A rational line is just a line in the plane given by an equation with rational coefficients or integer coefficients. The line y equals x would do fine. The line y equals x plus 17 would be great. The line y equals 15x minus 4, perfect. Any line defined by rational coefficients will do great. And now, finally, we're going to be doing this. Imagine we have a point on our rational line, and we move this point around on the line. We always connect it to our existing rational solution. So now we have a line and an ellipse. In how many points do you expect them to intersect? A line and an ellipse. In how many points do you think they intersect typically? Yeah, they're usually 2 points or 1 or 0. Typically 2. We'll see later how this works out, but 2 is generally what you expect to see. So this line intersects the ellipse in 2 points. One of them we're familiar with, because we always use the same point. It's the rational solution discovery. The other point is going to vary as we move our point along the rational line, right? But here's the trick. I can easily guarantee that this line will be rational. Point will be rational. Because I'm working on a line that's a rational line, it's very easy to find rational points in such a line. Just pick rational values for x and we'll get a rational value for y. So I can make this point rational. This point is rational. This was our first step. We made it rational. We found a rational point. What do you think about this point?
Rational.
Must it be rational? It's a good guess. But why?
Because if you write the equation of the line that connects a rational point to a rational line, it itself would end up coming out to be rational.
Correct.
And all the points along it.
No.
Yeah.
But that's very, very good stuff. A rational line doesn't only contain rational points. Like I can take the line y equals x, and I can choose x equals square root of 2, and then y equals square root of 2. That's an irrational point on that line. But how would you analytically, how would you find this point? What do you do when you find this point? You have to solve something. What do you solve?
Oh, you're solving the system of equations with the ellipse and.
Yeah, you're solving it, two equations. I need a point that is on the line and on the ellipse.
Right.
The ellipse is what kind of equation?
Quadratic.
Okay.
Quadratic. The line is what kind of equation? Linear. So I'm solving the system, and ultimately I will need to solve what sort of equation to find x, for example. A quadratic equation. With what sort of coefficients? Rational coefficients, because the ellipse is rational and the line is rational, just as you said. This quadratic equation has one rational solution. This one. What about the other one?
Can't be irrational.
Cannot be irrational. Why?
Closure.
They come in pairs.
Because you're thinking about complex conjugates, or
Yeah.
No.
Am I not thinking right?
everything here is real. But can a quadratic equation with rational coefficients have two solutions? One of which is rational, the other one irrational.
Because
Yes,
why?
closure.
If one was irrational, then the other one would be irrational.
Why?
Because the complex, like the quadratic formula, the plus and minus with the square root sign.
Yeah, that's right. That's one way to see this. Another way to see this is that the sum of the solutions is the coefficient of the formula, right? Or the product of the solutions, right?
Yeah.
So if one of them is rational and the product is rational, so is the other.
Like the product of the solutions of a quadratic formula.
Yeah. So if you have,
It comes from the coefficient. It's like the second of the.
if you have, let's say you have a quadratic formula like ax squared plus bx plus c equals ax minus t1 x minus t2.
Or the C over A.
Right?
Yeah.
This is a general form of writing down. This is a quadratic, general quadratic expression, and this is the same expression factored out, right? And if you just expand this out, so for instance, a times t1 times t2 is c, right? So the product of the solution is just c over a. You may have seen this before.
Oh, rational root theorem. Right.
Vieta's formulas.
Yeah.
Right.
Okay.
Sum
We're okay.
sum of the solutions is negative b over a,
I
right?
think in school no one ever calls them Vieta's formulas. It's just called roots and coefficients formula for some
Roots and
very
coefficients.
prosaic. Yeah.
Down with Vieta. We don't
I
like.
don't think I've ever taught that.
Yeah. Anyway, so like the point is,
That is.
because of these formulas, since we know the coefficients are rational, if one of these t's is rational, so is the other. Another reason is you said it correctly. Like we have the quadratic formula, right? Negative b plus or minus square root, blah blah blah. So either the square root comes out rational, in which case both are rational, or the square root comes out irrational, in which case both are irrational. So like there's no question. To go back to our little projective formula, if we vary this point on the line, we make sure that it's a rational point, which is very easy to do. And we make this projection, connect this line to the rational solution we have, and find the other solution. We are going to get this guy is always a rational point on the ellipse. Always. So that means, geometrically it now becomes pretty obvious that if there is any solution, there's infinite many. Just take any rational line, vary the point, keep connecting it to a rational solution and see where it intersects.
Now this obviously has to be pick a line that's not intersecting the point.
Correct.
Right.
You're right. Projection doesn't work if you happen to choose a rational line through that point. You're in bad shape.
Okay.
But
And
yes, right.
it doesn't matter if it intersects the ellipse or not the rational line.
It doesn't. No, it doesn't.
Yeah, you drew it so it does.
Right.
So it could be.
That's right. It doesn't matter much what this line is. Of course, choosing the line wisely can give us an easier time when we're solving all these equations, which is what you guys are going to do next. So let's go back to our circle of radius 1, our favorite circle of the day. Here it is. Now I'm going to have you guys just do it, but I'm going to help you out a little bit by choosing the point in the line for you. As I said, you can do it like you found a rational point already. For example, 3/5, 4/5. You can start with that. And you can pick any random rational line. You can solve this, but that may be a little bit unwieldy. So let's pick a simple rational point. And I'm going to choose this one. Just because I've done this before and I know that this is a good choice. Okay? This point. -1, 0. Alright? So this is my purple point from here. And as my rational line, I will just pick the line. This one. The line x equals 0. So how do you find a rational point on this line? Just pick a number t. A rational number t. So what is this point? What are the coordinates of this point? X coordinate is going to be 0, and y coordinate is going to be my t. Very simple. So 0t is a very simple way to just find rational points on this line. Now, what does the procedure tell us to do? We have to connect with a red. We have to connect this rational point that we have to our parameter, and whoa, we're going to get another point in the circle, which is guaranteed to be rational. And as we vary this t, this point is going to vary along the circle. Does it cover the whole circle? Let's see what happens. When the green point when the green point is over here, where is this red one?
Same point.
Right there. As I decrease t down, what does the red thing do? It goes here, right here, until I get over here and they meet again. So the green point is here, the red point is here. When the green point is here, the red point is right there, right? And what happens if I keep going? Up or down?
Well, as you approach infinity, you'll...
Right, so if I pick the green point here, above the circle,
Still touching.
it still works.
Yep.
It's just the yellow, the red point just moves over there, right? So as I throw my t way up there, this red point is going to approach here. Is it ever going to make it all the way here?
No.
Not quite. I have to throw t all the way to infinity to make that happen. So the one point I'm going to actually be missing with this procedure is the very point I started with. I'm not going to get this one, but I am going to get everything else. So this red point is going to be moving along the circle, and it's going to have a really hard time getting close to here, which is a little bit like what you said before. Right? It's hard to find those rational points close to the axes. But it's going to work. If I throw, like if t is 1,000, I'm going to get a point very close to this one. If t is 1,000,000, it's going to be even closer. And the same when t goes down. So what I'm going to have you do now for like 15 minutes, because this is a calculation that every person should see, is this one in the lab, is just do it. Meaning, find the equation of this line. Determine where it intersects the circle of radius 1.
But so we're using that equation, x squared plus y squared equals 1.
Yeah. You're starting with this equation. This was the in our Diophantine analysis problem. I gave you this equation as a polynomial equation, and I had you find rational solutions of it. What you did, well, I did this, but next time you're going to do it, is you found a point, -1, -1, 0. You chose a line, and you did the projection. And the point is, as you do it, you're going to be intersecting a line and a circle. And there's going to be two solutions, one of which you already know. You just have to determine the other. And you guarantee that this other one, is going to be a rational point of the circle. So please, just do it. Go. Is the task clear?
Yes.
Okay. Let's try and do it.
No, so you have this point and you get the equation.
Yeah, we
of y
need to find the
equals
equation. Yeah.
So this
Or we
t,
can-
the y-intercept.
The output of this process
Equation of y equals t.
Yeah.
is going to be
And then you're
Maybe
doing
you
a
are.
system of equations. that-
Parametricize it, and then
some formula here for this point.
I'm
Oh,
finding the general
formula,
equation.
you said, so
Whatever.
in terms of t.
Yes, t is going to be a parameter right here, because I get to choose t. And as soon as I choose t, the green point is fixed, and then the red dotted line is fixed, and then this point is fixed. So it should have some formula depending on t. T is a parameter. It's a rational parameter. You can. There's more than one way of doing this. There's other way.
Which one would you rather?
I think this is easiest, but I mean, I think I like the one where you just leave this and the equation of that line. And the trick is you don't have to actually solve the quadratic equation. You know what to do. You can actually figure out the other solution just using these forms. By the way, you guys can use this. When you do this and the analysis problem, you're going to have to solve a quadratic equation eventually. Use these formulas. When you have a quadratic equation, one solution of which you already know, you can figure out the other solution much easily than using the formula.
But it seems like I lose a chance to check anything. It seems like
That's right. But if you figure this out correctly, you have a built-in check in the end.
okay.
You'll have some x and y's here depending on t. Square them, add them, and see
So you, right, I see. And so you kind of, and so you make sure you pick a point per square.
And if you've done this before,
That's probably how
sorry,
Mathematica does
but
it.
I hope to have like other stuff you haven't seen
Right,
before.
yeah.
coming up.
Right, exactly. I get it. Right, yeah. Right. That's nice. Yeah, simple. Josh and I are wondering about if this were a practical method used in like a computer graphics. There's of course the problem of the non-uniformity of your dots and what the real world algorithms are for making reasonably uniform dots.
On what?
Well, on anything in a way.
So most computer algorithms are drawing splines, B-splines, which are
What if you have something where you can't easily solve for one variable?
yeah.
I got an imaginary
I guess it depends
solution.
on what it is. If you give Wolfram alpha,
So you got y equals
Yeah,
x
I'm
plus
not
t.
on here.
just a random equation, but it uses a bunch of characteristics. It samples
So
and it
this
sees
is my A.
how it's doing, and then it resamples if needed.
That's what I thought. It kind of like takes big chunky things and does some bounding to say, does the curve pass through this
I
block
think
of
it
stuff or
it
not?
starts with like slicing the desert to see like where
And then
it
it
is,
throws
but
away
then
the
when
ones
it
it misses
gets to
and it
sampling, I think it just uses heuristics and like maybe it uses derivative to see like how.
Right. The sort of things you'd expect to try to do.
Right, it's heuristic. I'm sure there's like a legal theory around it, like how to do it well, and I'm
Right.
familiar with it, but there's obviously no single way that will guarantee anything.
Right.
You can always find exotic. Like I've actually, on my way to one of the previous circles where I wanted to talk about this, I wanted to show some like crazy formulas. So I took my iPhone and I typed in formulas in Wolfram Alpha. And if you make it crazy enough, you can make it go crazy. Like it starts plotting something, then it goes like completely loses like
Well,
any sense of where it is. And
I got a real Wolfram Alpha fail yesterday when Lieutenant Shubin was giving a talk about the chromatic number of the plane. And so I typed in chromatic number of plane into Wolfram Alpha, and it misinterpreted it, which is fine, but it also gave an answer 4.
maybe it's right.
Maybe. But then it showed a picture. It just showed a picture of a plane.
Oh, sounds
Okay.
So I took off. I gave it a D because I said show work.
So I had it's interesting that you mentioned this. I was just thinking about it, and I had maybe you guys know.
The
So
chromatic number of the plane.
No.
I don't know.
So there is I think fairly difficult theorem of Erdős and someone else. It says that the chromatic number of the plane is achieved on some finite subgroup. Is there a good example of an infinite graph whose chromatic number is larger than any of its finite subgroups? Like if I wanted to convince people that this is not an obvious statement, I would want to show them some infinite graph that is not 3-colorable. Every finite subgraph. So it doesn't work with 2 colors. Unfortunately, every finite subgraph is 2-colorable, and the graph is bipartite, even as an infinite graph, and it's 2-colorable.
Oh, factor in 2.
But 3 colors maybe. So like
Right. Now I understand the question. I don't know
now
the
in the
answer.
plane, this is I think this is hard. In the plane, like the chromatic the graph of the plane. It's not a good example.
Right. I think the place to start asking that question would be looking at Seufer's mathematical coloring book, which has probably it probably has the whole encyclopedia. Do you know about this book? Do you know Seufer?
I know that Seufer wrote papers with Scheller that demonstrate that the kinetic number of the plane
Depends on
may depend on
axioms
axioms.
of choice.
So I'm not surprised he's a coloring guy. But I
Right,
haven't seen
right.
it.
Well, he wrote this giant book, like 500-page book, that's a combination of history and math. And it has at least one mistake, and it probably has a lot of mistakes in it. But you found one? Well, because I was trying to look something up that, and I actually followed one of the read one of the proofs he wrote. The proof was wrong, but it's a minor thing, because it's impossible not to make mistakes. But yeah, it's a very nice book. It has everything you wanted. But if you know Seufer, he's kind of, you get more than you want. It's like but it's like a really great encyclopedia. Now I had a question about your vector thing. So the relationship between A and B, is there any important relationship? So then why not just lexigraphically order with some order your A vectors, and then just
There are more B's than A's, so
yeah, and then
order them and then take the first one to the first
right.
Do
one.
it.
Yeah.
What's the computation? I'm giving you the A's. What are the B's?
So
Well, you convert the A to an integer, which is its
How?
index in lexicographic ordering. That's not hard.
Okay, suppose you did that. How do you
But
find
the
the
inverse process is a little harder.
It's not only
Not
harder,
so bad.
but whatever process you use to like enumerate, or like get or enumerate 21 tuples into integers, you can, but then there's no guarantee that so you map the 20 to an integer, and then you inverse map it to a 21 tuple. But why would it be confined to the range 1 to 100? Like, I don't know if any...
I'm just saying I'm going to enumerate all the tuples that
Wait,
fit
wait,
the
wait,
criteria
wait.
that are
So-
increasing and in the range 1 to 100.
But you enumerate the 20 tuples and you
And the
enumerate the 21 tuples. But how do you... So either you have a formula, or you have... Like, you can't store it in memory.
I'll say an algorithm, not a formula.
An algorithm. So, like, give me a good algorithm to do that. Like, I don't know of one, to be honest.
So that part of the puzzle
I
is
don't think that part's hard, actually. I think I could sit down right now and write the computer program.
Okay. So I'd love to see it.
So the question is, 20 tuples.
so
Increasing?
Strictly
yeah, strictly.
The increasing part is that's one way of
Well, just saying that
it's
discrete.
So you have basically you have sets of 20
plugging in
integers 1 to 100,
numbers.
and for each one you have to find
I didn't play with any numbers.
are we supposed to do 21 tuples.
I use actual
Also,
numbers.
We should have 500, right?
So you get
such
one
that the map is 1 to 1.
Right,
Obviously not
it's
one because there's more in the second set.
I didn't
Yeah,
try
so
with
now
T,
you
I
just
tried
pick a value
actual
for
numbers.
Implemented
Right.
function
I
as
mean, I kind of figured. I was just thought.
code that
Like
We're
I
supposed to
made
actually
T a
just
half,
plug in a bunch of numbers and.
I think you said just find one point, or well, yeah, I mean, you can do it infinite
Do you
times
use
if
actual
you've got
numbers?
lots of.
So the order doesn't matter, but the function
No,
I can just do that.
Order doesn't matter, just assume that the input is given. Increasing order of the output is also.
You can use a number and make it work.
Well, you can use a number, but you get just one value. If you use T, you get a formula for which
No,
then
but
you
my
can.
value was irrational.
Which is a vague statement, I know.
It was supposed to be rational if I had a rational.
I see what you're
Third,
saying,
third
but
third floor for men's golf.
There's 2x.
Hey, can I ask you a question? What are those formulas? The sum and product? Who are they due to?
yeah, the equation
How do we know them to be true?
Yeah, like so if that's
Just
what
expand.
I went,
Just expand.
that's what happened over
Well,
one.
for a quadratic.
Oh,
but what about for?
I know
Still
what
just
I'm saying,
expand.
if I put in numbers, it should give me a rational
You always
answer because these are rational.
Right, you'll find.
What is the
So the easiest way is to
wasn't Newton
already.
This one I
responsible for
have.
some part of the generalization of
I'm gonna try just the regular, so I got T over 1. So TX.
T equals 2?
Because if
T equals 2, then
No,
x
that
equals
is
negative
X.
Some of those symmetric function identity things
You
are
should say up T over
anyway.
1.
I don't know what.
Oh, right, right.
No, but actually,
Some of them are Newton sums.
So now
yeah,
there's
so for this line is T.
So for example,
I went up T.
the product, when you open up, when you expand this product,
There's only
Nice
one
stuff.
expression that has no
I've noticed that. Even some of the really young ones.
Negative 1 to the n.
Because then you just make random values. Then, so like 3, 4, 5 is a Pythagorean triple.
8, 0 is always the
35, 36, 37 is a Pythagorean triple.
Now, let's see what happens with the x.
6, 35,
Get a
36.
x
No,
here.
I think 35 is 6.
This x, for example, and all the other 9.
I didn't know what to do.
Or this x.
35
Think about that.
plus
So
something.
the coefficient of x is 1.
Is a Pythagorean triple.
Yeah, but it doesn't have to be onto. So I mean, obviously,
Oh, I missed it. I thought you wanted
All the
any
alpha
20
i's.
any 20 is in the range 1 to 100.
Oh,
It gives you
one to
it gives you a
So
21
you can use this to generate
Also in the range
Pythagorean
1 to
triples,
100.
and you're just using random values.
Add this up.
That's 1 to
Well,
1.
this is a small side.
So it's like, it's like alpha 2, not alpha 4.
This
Alpha
one.
1, alpha 3.
Well, not the small side.
Right, they have to be
Small like
put them in strictly increasing order.
Skip 3, alpha 4, alpha 5, alpha n. So the sum of all of this, every time I'm just missing alpha 1, missing alpha 2.
I meant small side like smaller than the hypotenuse.
Add them up.
Small.
And there's also going to be a
In
sign.
my Conic method, it's not very hard to extract the function.
Sorry, terminology.
No, but I mean, that's not
It's
small.
alphabetical order.
No, when I said small, I
A1.
meant
You just
smaller
mean
than the
non-hypotenuse.
hypotenuse.
Oh yeah, that's
So you write that function and it's in
Like,
there.
for example, the coefficient of the
well, that's good.
x to the n is x
So
to
with
the
my kids
n.
and algebra,
The only
and
way to get
I
x
like
to the n here is just x, x,
I'm
x.
so horrible with using
X to the n is
proper
simple.
terminology.
This one is
Because I'm just always
So you
thinking
make x to the n
the
minus
top
1.
and the bottom.
X is the
Bottoms are the
same.
same.
Set
Top
one.
ones are the same.
So this is simply a
Right.
So this is the product of all the alpha.
Right, when you know
This is
that
the sum of all the alpha.
Right.
Next one is 3. It's called the elementary symmetric function.
you write the 99 stuff and I assume it will start with 1.
I think it's product of length n minus 1. All of them.
Some kind of recursive logic like that. I don't think.
I know you're
All of
done.
them having the same sign.
The lower part.
All of
Let's
these
look at the lower part.
So as soon as you accept the 1, it's with the number between 1 and
So I just did this.
How are you doing?
No, they're not only in solving this thing. It's not like you can solve an equation by using the derivative. Because if you try to solve this equation,
So
you
that
take
means
the
if we
original
pick a
product.
T,
It's not-
Actually,
You try to begin with quadratic.
no, but it's
When you go to which one it is, rather than trying to number sorted.
I mean, if you were to do this computation,
So there is here,
It kind of sounds like the card strand where your assistant is given 5 cards and you put 4 of them out of the table.
So be more than
So if you
right
get
side.
you can combine these together.
then
Right, which is what I
product
was
of
gonna
the
ask you. That's my question.
Yeah, and I think when you check some things.
How are we doing?
Sure. I mean, imagine correctly a function that given 20 adds to 20 first and that's not equal to that.
when you know when your space x equals
To make sure that it
because
actually is
if
1
you're
to
going to
1.
do this computation, you'd have
And
to
not only
just
it actually is 1 to 1, but you can figure out which number it was.
Oh, yeah, I'll get this in a second. It's good for you. Folks, show of hands. How many of you have some formula for me? Cool. So let's keep going. Okay, that's okay with you? Is that okay? Yeah. Let's keep going. Sorry, we had a digression here about Vieta. Okay, suggestions. Who wants to give me the solution, and then we can talk about how you got to this. Any volunteers? What's the x? Yeah.
1 minus t squared over 1 plus t squared.
1 minus t squared over 1 plus t squared, and the y?
I guess I forgot to do that.
All right.
I don't know how
Well, the
it
y is
goes.
just your
Anybody have a
equation.
y?
Y equals tx plus t.
Yeah, but we have x already. That's correct. That's correct. But can we?
Oh, wait,
So
just plug that in.
I'll help you out. Here's one. So let's try and summarize what we have so far. So one of our original quests was how to draw a circle, and by now we have several formulas for it. So we had this one, x squared plus y squared equals 1, and its cousin, this guy, have a fancy new one. X is 1 minus t squared over 1 plus t squared. And y equals 2t over 1 plus t squared. As I said before, this last one is as good at doing circles as any of the others. Sampling-wise, to a question that was raised, sampling-wise, uniformity-wise, it's horrible. Because if you take t here and you sample it, what do you think the circle is going to look like? I'm going to get this right this time.
It's very dense on the right.
Where is it going to be dense?
On the right.
Right.
On the right side by the x-axis.
Yes.
Because we started with the point on the right. If we had started on the top,
Yeah,
it would be more dense on the bottom.
let's do this. Let's take on only integer values. Very simple sampling. T is 1, 2, 3, 4, 5, 6, all right?
Those sides closest to the
Well, that's not very
rational
good.
solution.
So, just as an example, if this is 1, our circle is just here, right? Tiny circle. If I do a very dumb sampling and I only take t to be 0, 1, 2, 3, 4, 5, or -1, -2, etc., etc. So one thing is going to happen. I'm going to miss this whole section of the circle completely, except for this point. For 0. For 1, I'm going to get this point. For 2, this one. For 3, this one, this one, this one, this one, right? So if I sample with t's, which are just integers, I'm going to get a beautiful arc over here on the left. I'm going to get absolutely nothing over here on the right, except for this one point. If I do a better job sampling, like let's say we have half integers, then I'm going to get a few more points in here. But however I do this, if I do a uniform sampling with t, I'm going to get a very lightly populated right-hand side and a very densely populated left-hand side. Okay, is that okay this time?
Yeah. Very cool.
So it's not uniform. So these formulas, for the purposes of computer graphics, like actually plotting circles, are not very good. But there's one wonderful thing about them. They are by far the simplest of the lot. Given t, getting to the x and y here is child play. There's no extraction of square roots, definitely no trigonometry involved. All you do is take your t, square it, divide, you get your x's and y's. This is called the rational parameterization of the circle. It needs to be better known. I don't know why very few people are familiar with it. Somebody pointed out before that when you do those things, it's very easy to get it wrong. So it's very good to check yourself. How can we check that this formula is correct?
Square both and add them together.
Square both and add them together. Let's do it. One minus t squared over 1 plus t squared squared plus 2t over 1 plus t squared squared. So at the bottom I'm going to have 1 plus t squared squared, and at the top, luckily these two fractions are the same denominator, so there's no need to multiply anything. And here we have 1 minus t squared squared plus 2t squared. What is that? Expand it out. What do you get?
2t to the 4th minus 2t squared plus 1.
Let's do it. 1 squared is 1. T squared squared is t to the 4th. And I have a negative 2t squared here.
T squared plus
Plus
1 squared over
4t squared, right?
t squared plus 1.
So put together I get a 2t squared here, right? You guys see that?
Right.
I had a negative 2 here and a plus 4 here.
Factor.
Miracle. This is exactly what is the numerator? 1 plus 2t squared plus t to the 4 is exactly 1 plus t squared squared. You can see that?
Figure 1.
So you get 1 and t to the 4 and 2 times t squared. Now my numerator and my denominator are the same thing. So this is just 1. We have here, magically, two rational functions that when when you square them and add them up, everything cancels out. You just get one. Very neat. Because we have three formulas for the same thing, they gotta tell us something if we put them together. For example, these two, the first two put together, what do they teach us?
Sine squared plus cosine squared equals 1.
Yeah, so the first ones put together teach us something very, very fundamental about trigonometric functions, which is the cosine of t squared plus sine of t squared is 1. Very useful fact. What do you think I get if I try to combine these two? Well, I should have done this.
Sine t
It's
equals
not
2.
the same t, right? I apologize. The t parameter used to parameterize a circle with an angle, and the t we're using here, which is just the height of this point, is not the same thing. Have you guys seen this relationship before? If this is our point, this is theta from the trigonometric approach, and this is t. What is this angle?
Half theta.
Half theta. So what is t? This is 1. What is t?
Tangent of
Trigonometry.
theta.
Tangent. T is tangent half theta. Have you guys ever seen this?
I don't.
Have you guys ever seen this thing?
Yeah, but
When you do, for instance, integrals of trigonometric function, this is a very useful substitution. And that's why. Because when you have an angle theta, and you find t to be tangent of half theta, then what is cosine of theta? From here. X is cosine of theta, which is just 1 minus t squared over 1 plus t squared. And sine of theta is nothing other than 2t over 1 plus t squared. So we have here a trick of converting trig functions into algebraic or rational functions. For example, suppose I'm having you solve a trigonometric identity. Are we still doing this in high school?
Yes.
It is when I was in high school. You get some funky formula with cosines and sines of stuff. And you want to show that it's an identity. Right? That it's always true. And it's very, very tricky. Because you typically with trigonometry you have a variety of different formulas you can use. So you're not sure what to do. And so here is a mechanic procedure for proving any trigonometric identity. Define t to be tangent of half theta. Out of the blue. I just want to use this substitution. And then cosine of theta turns out to be this. And sine of theta turns out to be this. Plug these into your identity. And instead of having a trig identity to prove, you have a polynomial identity to prove. How hard can that be? Just expand everything out and everything just cancels out. It's got it. I have a book about Solomon and Tate that talks about rational points of elliptic curves, and when they show this, they actually say this in a paragraph. If we had taught this to high school kids, the whole subject of trigonometric identities would become trivial. So my conspiracy theory is that this is why we don't teach that. Because then we won't have trig identities to have them work through.
Well, and in a larger sense, trigonometry, except if you're not using trigonometry to do things with triangles in the old-fashioned way, trigonometry is a tautological kind of middleman. It's not. There isn't content to it because, like you say, you get cosine squared plus sine squared equals 1 for free, as it were. But it actually you already had it in a sense because you could just think of the trig functions just defined to be the coordinates on the surface.
No, I agree, and I actually think trigonometry is a good exercise, mental exercise for students because it is nice that it doesn't have necessarily an algorithm. At least if they don't know the algorithms, then there's a variety of things you can do, and it's nice to work them through like something that is not like formulaic the same way that the quadratic equation is. But you're right, trigonometry is not really necessary for anything else. Yeah.
What about when we get to integrating trigonometric functions.
Right. So
Would the same substitution principle work here?
yes. So when you have an integral involving trig functions, you can do the same substitution. We should figure out what this means about d theta and dt, and I forget. Anybody remembers? I'll figure it out after the break. I'll figure it out for you guys. So like if you have an integral, it has cosines and sines, and it has a d theta in the end, right?
Right.
And I'm doing the substitution, then I can replace every cosine of theta with this, and every sine of theta with that. I only need to remember to replace d theta with something dt, and I just forget what it is. So I'll figure it out and let you know. But once you do that, your original integral that had those scary trig functions in it becomes the rational function integral, which presumably is easier. It is. So this is how you do integrals of trigonometric functions.
I was actually thinking about when you have an integral of, 1 over the square root of 1 minus x squared. In those cases where you do the trig substitution,
right, that's
to make it easier.
Yeah, that's almost a reverse approach. It's a very useful trick as well, but that's not what we're learning here. Like it's not the side benefit that we got from this particular set of equations.
Okay.
The side benefit is this guy.
All right.
And if you scan your integral books, also I think your trigonometry books, like this is in many problems in trigonometry, this comes out to be the easiest way to solve them. And the point is, this is almost always a way to solve anything, because it converts trigonometry into just polynomial form. Right? And I was taught this in high school, I remember, but nobody ever explained to me why tangent half theta. Where does this come from? Right. This is where it comes from. This relationship between theta as the natural parameter of the circle, and our t, which is a rational parameterization of the same circle. Now we did this now for the circle, but as I explained before, this procedure is fantastic for every polynomial equation in 2 variables of degree 2 quadratic. And remember the procedure. You have to find one rational point, and once you do that, pick a line and do the projection. And you guys just did it for this one.
And that procedure is called the Diophantine analysis?
No, Diophantine analysis is the whole field of taking equations such as those and figuring out what the rational solutions are.
Okay.
The procedure, does this have a name? It has a fancy description in algebraic language, showing that every conic section, every quadratic curve is birationally equivalent to the line. So like the ellipse, from the point of view of a number theorist or an algebraic geometer, an ellipse is a line. A hyperbola is a line. A circle is a line. When I say is a line, I just mean that this line and this circle are mapped to each other by rational formulas. So there's no difference between them from the number theoretic point of view, which is just what we did here. If I had to do the same thing for, what's the next circle you want to tackle? Here's another circle. Looks pretty much like the first one, but its equation is this one. How would you find all the rational solutions of this? One of the things about Diophantine analysis is that equations can look very, very similar and be very, very different. So all I did was change the 1 into 2. Can you do this one? What's the first step? We have to find one rational point. Can you give me one rational point here? -2, 0. 2, 0 doesn't work. Right? There is one. It's not hard.
Oh, which one?
1, 1. Exactly. This one. When x equals 1 and y equals 1, the sum of the squares is 2. Perfect. So we have a rational point. Like I said before, this is sometimes the hardest part, and we'll do this in a second. We have a rational point. Which line would you pick? We can pick the same line we can do it with the same line as we did before, but it's kind of breaking the symmetry here, right? Because the point is here, and if I'm taking this line, it kind of looks like, there's a better line to pick.
Y equals
Y
negative x.
equals 0.
This one, yeah. That's going to work better. So we do the exact same thing. We take a rational point. This one's a green point. Sorry. We take a rational point on this line. Very easy. It's the point t negative t. For any rational t, this is a point on this line, right? T negative t, a rational point on this line. And we connect it to our one given solution, wherever it is. And we solve, just like we did before. And we're going to get a different pair of rational formulas for this point. And so we have now parameterized rationally the circle of radius square root of 2. This one. Don't do it now. This will be your homework. If you did the one before, it's the exact same thing. You see why this is the exact same thing, right? Okay, what's our next circle?
X minus 1 squared.
I'm going to stick to the circles around the origin. Which one do you want to do next? 3. Okay, this one I am going to have you do right now. Remember the procedure. Find the rational point, pick a rational line, connect the stuff, find the intersection, solve. Yeah.
Can't do it.
Sorry?
Can't do it.
Why not? Just one.
3 can't be written as a sum of squares. We learned that yesterday, didn't we?
You did?
I think we learned that 3 can't be written as a sum of squares from Tatiana. Didn't we?
Well, sum of squares of integers, sure, but what about rational?
Wait, 3 can't be written as a sum square of the integers. That's too easy. She must have shown you something a little bit more clever than that.
Well, we were just doing
You were just drawing on
areas
grid
of
paper.
squares in grid paper.
Okay.
So we only, I suppose, had integers to work with.
Okay. So the class has a suspicion. What's the suspicion?
There are no rational.
So the
That we-
suspicion is very strange. The suspicion is that the circle of radius square root of 3, as opposed to the circle of radius 1, and as opposed to the circle of radius square root of 2, from the Greek perspective, is empty. Remember, we talked about early in the class we talked about the line, the number line, and how it has all the real numbers on it, and the rational numbers are kind of dense. What do the rational points on the plane look like? If I had you plot for me the rational points on the plane, what would you do? What do they look like? All the rational points on the plane. Where are they? 1, 1, 1 half, 1 half, 3/5, 4/5.
Right.
Something like that, right? Roughly. Do they miss any region? Are they absent from any region?
Apparently that circle.
Well, region. Are they missing any, like, is there any gaping hole in the plane where I can't find any rational points? The answer is no, because it's very simply, if I have a rational point here and a rational point here, I can just find rational points in between them just by dividing. Right? So they're dense. Any way you look, there's tons and millions and infinitely many rational points anywhere. But this crazy circle manages to sneak in between them, not touch any of them. It's just a circle. It doesn't touch any of the rational points. It's a whole curve. Yes, it doesn't have an area. Nothing with an area can avoid rational points. But it has a length. It is visible. But it's invisible to the pre-Pythagorean Greeks. There's nothing on it.
No, you haven't proven that.
No, not yet. You guys are going to do it.
Wait, you said it doesn't have an area, but wouldn't its area just be the pi r squared?
No, I said I didn't have an area. As a shape, it's a curve.
Oh, true. Okay.
The circle, the disk. What do you call this? The inside of the circle. What is it called? The disk. So this disk, which does have an area, certainly contains many rational points. Right? Many. But the curve, the perimeter of the circle, kind of sneaks in in between them, which is really hard to do because like they're dense, right? But it does that.
Would that be related to the countability, non-countability? I mean,
No.
if you think there's countability, non-countability, that means it's not exhaustive, and it must be
It's a good point.
infinite amount of spaces that are in between the.
That's a totally good point. The power, the cardinality of rational points in the plane is aleph. No, but it's countable. So there's definitely way more non-rational points on the plane. Yes, it's still pretty neat feat to sneak in between them without touching them. But you're right. Just having the countability argument doesn't tell you that some curves touch the points and some curves don't. Because this circle looks geometrically exactly like that circle.
But it would tell you there's an infinite amount of points that fall in between them, right?
The procedure we've seen before, the one with this thing, tells us one thing. A conic section, if it has one point, it has infinite length. If it has one rational point, you can actually parameterize the whole thing with rational points. But it doesn't tell you that all conic sections have a rational point. Here's one that I claim doesn't, and you suspect doesn't. So prove it. Any problem with rational numbers is more easily tackled as a problem with whole numbers. Just write down the fractions and multiply them out. Anybody talk to you about quadratic residues? No, I don't think so. But like modular arithmetic, like working modulo something. Is that something you've seen before? Modulo 3, modulo 4. So think about this stuff. Yes?
Isn't there a method of using Diophantine equations and Bazoo relationships to find a solution to this?
No. So there is a method of determining whether a conic section has or doesn't have a rational point. I don't think it has anything to do with Bazoo. It has something to do with p-adic numbers. And we can also talk about these if you want. One thing to know is this is, as I said before, this is far harder than the second piece. Once you find a rational point, the mechanical procedure that you guys did before, it's annoying, it's kind of a nuisance, but it's like a mechanical procedure. It's not hard.
Right.
This is harder. Figuring out if there is a point. And in the next, after the break, we'll talk about equations of higher degree. This becomes like completely unsolved. For most equations that are not conic sections, if we go just one degree up to cubic equations, nobody knows how to figure out if there is a rational point. The zoo relations, I'm not sure. So the one procedure I know, it has to do with p-adic analysis.
I have the procedure at home somewhere. I just can't.
Okay.
It's been a long time since I've looked at it, so I could be misremembering.
Yeah. Okay. But let's try to figure out why, if it's really the case that this circle doesn't touch any rational point. Let's think about it. Then we'll work through the solution if you find it, or if not, I'll show you, and then we'll take a break and we have another hour to do some other stuff. These two circles certainly look the same, don't they?
It was very round.
What's the other one?
You're good at drawing circles.
Similar.
I never was. I'm not sure what's wrong with me today.
Tatiana was really good at drawing circles.
Someone mentioned this.
Really big.
When I said that I said that this class is how to draw a circle. People thought that this is going to be a challenge of like standing in front of the whiteboard and doing this. And someone said Tatiana's going to just kill you. I guess he's good. My grandfather was really good at that.
Was he a mathematician?
Hmm?
Was he a mathematician?
He was a math teacher, yeah. He never got a PhD. He went to Germany to do his PhD, and as he was about to finish it, someone scooped him. Today, I think if this happens to you, you still get a PhD. But back then in Germany, early 20th century, no way.
Still was.
Yeah, somebody like published a paper, I guess, about the problem he was working on. I think it had to do with Beaver conjecture or something, and like.
Oh. That's cool.
multiple of 3 can't be a sum of squares.
A multiple of 3 can't be, well,